If a matrix was invertible, it meant that your matrix had a pivot in every column. It means you have a pivot in every row, because invertible matrices have to be square, and that means you can solve any square system like this for any right-hand side. So why don't we just go ahead and use this formula that I've written in the box? Now, even before that, not every system we ever solve is square, so it doesn't really make sense to talk about an inverse. But even if it is square, a lot of it depends on how we actually find the inverse of A, based on the idea that we talked about above, that you can row reduce your matrix to the identity. Now, we talked about row operations using matrix multiplication and elementary matrices. So that's all going to help us here, because it's going to give us equations rather than this vague equivalence symbol. So when I say that a matrix is reducible to the identity, it means that if I start with my matrix, I can do a bunch of row operations. So these elementary matrices I'm going to represent by these E's. So there's going to be a bunch of these different operations that take me to the identity. By definition, this thing right here is equal to the inverse of A. What that means is that I am allowed to write this thing here. And not only am I allowed to write that thing there, a key understanding point is going to be that I could take all of those operations and then multiply them by the identity. And so here's an incredible connection. All of the same steps that I use to take the matrix A and turn it into the identity, those are exactly the same steps that will turn I into A inverse. So whatever I do to turn A into the identity, I have to do exactly the same thing to the identity to turn it into the inverse. So we get a nice little procedure. So if I want to find the inverse, I'm going to start with my matrix A, and then I'm going to augment it with the identity. And then I'm going to do row reduction steps. I know if my matrix is going to be invertible, it will end up being the identity. At the same time, I'm going to perform those exact same steps on the right-hand side too, the identity matrix. And if my matrix is invertible, the answer that I get here is going to end up being the inverse matrix. Whatever steps you do to get to the identity are going to turn out to be exactly the same steps that will take you from the identity to the inverse. So to try to show this to you, I'm going to start with a matrix 1, negative 1, 1, 2, 1, negative 1, negative 2, 0, 2. This is my matrix A. Now I want to see if it's invertible. So what I'm going to do is augment it with the identity matrix on the other side. And every time I do a row operation, whatever I do to one, I'm going to have to do to both sides. So I'm going to start the process of row reducing this to the identity matrix on the left, and then whatever I get on the right will be my inverse. So I need to take negative 2 bunches of row 1 and add it to the second row. So I'll get 0, 1, negative 2, and I'll get a negative 2 and add it there. So you see, whatever I did to row 1 also has to happen on the right side. I'm going to take negative bunches of the top row and add it to the bottom. So I'll get a negative 1 here, positive 1 there, negative 1, 0, 1. And so I keep going about this. So I'm going to take that middle row and add the middle row to the bottom row. And when I do that, I'll get a negative 1 and so on and so forth. So the more I follow the steps, the closer I get to the identity. Now again, the matrix needs to be square, but not every square matrix will be invertible. So I see that in the bottom row, I am very close to what I want, the identity matrix. So I'm going to start eliminating zeros above that pivot. So I'm going to take 2 bunches of the bottom row and add it to the middle row. And then I'll take negative bunch of the bottom row and add it to the top row. I'll get a negative 2, 1, and 1. If I add the middle row to the top row, I'll get 1, 0, 0, 0, 1, 0, 0, 0, 1. So the bottom row stays unaffected. And again, if I add the middle row to the top row, 2, 0, negative 1. So the point of the story is that I finally achieved my goal. I took A augmented with I, and I now reduced it to the identity. The result that I'm left with is the inverse of the matrix A. 2, 0, negative 1, 4, negative 1, 2, 3, negative 1, negative 1. Sometimes I won't be able to find it. So for example, if I give you a matrix kind of like this, I can augment it by the identity on the other side. If I follow ahead and I go through and I do my row reduction, what you're going to find is that eventually you'll see something like this, that as soon as you see a 0 row, that means I cannot reduce this to I. So this is an example of a matrix that does not have a pivot in that spot. It has a 0 value. And that means that this matrix A is not invertible. Now we're ready to go back to that discussion that I had earlier. If I have a square matrix A and I have this equation, why don't I just use the inverse and solve this problem with a matrix multiplication? Why can't I just solve every problem like this? Well, the real issue is to find A inverse, we still need to do row reduction or Gaussian elimination. Then we have to do a matrix multiplication. We have to take the inverse that we found and then multiply it by B. It costs me more work to solve the system with the formula. If I just have a system AX equals B, in order for me to solve it, I have to do row reduction anyways. So why am I going through and doing this extra step of trying to come up with the formula? For everyday problems like this formula that we talk about isn't really useful. We do need this concept of invertibility, but it is not a computational tool. If you want to solve things by hand, solve a system by row reduction. It's cheaper.